So, what is vibration? Well, vibration is the mechanical oscillations of an object about an equilibrium point. The oscillations may be regular, such as the motion of a pendulum, as shown on this illustration here, or more random, such as the movement of a tyre on a gravel road. The important thing to remember is that it's a periodic signal. To understand vibration, we measure the amplitude, the frequency, and the relative timing. The relative timing is often referred to as phase. Okay, when we look at the amplitude of a vibration signal, consider the actual sine wave as illustrated here. We can describe the amplitude of the signal as a peak value, which is the maximum level in one direction of the wave, peak to peak value, which is from the maximum positive to the maximum negative value, or equally we can consider the RMS value, which is probably a measurement of the overall power in the signal. The frequency is the amount of times an event happens in a given time period. So, in general, for vibration, we measure the value in hertz, which means cycles per second. So, how many times did the object go complete a complete cycle? In this example, we can see that 2 cycles took 40 milliseconds. So, taking the reciprocal of one cycle, i.e. 20 milliseconds, gives a frequency of 50 hertz. When we talk about rotating machines, we sometimes consider looking at CPM, which is cycles per minute, and this allows us to easily compare it to the RPM of the machine. To understand the relative timing of a vibration signal, we look at what's known as the phase. So in this example, if you consider the pink signal as our reference, we can see that on the first example in the top left-hand corner, the green signal reaches its maximum and minimum at the same time, and this is considered as being in phase. If we look to the right, we can see at the point of the maximum phase, maximum amplitude of the pink signal, green signal is actually at its minimum, and you can see that there is conversely, it reaches its maximum amplitude at the same point as the pink reaches its minimum, and this is deemed to be 180 degrees out of phase. If we look out on the bottom left-hand corner, we can see our datum signal reaches its maximum at this point, whereas the actual green signal actually reaches its maximum sometime afterwards. And in the terms of degrees, it's actually 90 degrees. As it's later, it is known as a phase lag. In the final example, you can see that the actual maximum that the green signal reaches happens before the pink signal. And this could be described as a 90-degree lead. However, in vibration terminology, we always refer to phase differences as a lag. So in this instance, we would look at this maximum and say that it actually lags the pink signal by 270 degrees. Okay, let's consider 2 types of vibration: free or natural vibration, and forced vibration. So first, let's talk about natural vibration. So if you consider any object, large or small, will have its own natural frequency that it will want to vibrate at when any energy is imparted on that structure. So let's consider the guitar string being plucked. When that energy goes into that string, it will resonate, it will vibrate at a frequency that's dictated by the spring tension and generate a sound. We change the tension, we will change the sound, and change the natural frequency. So the string will continue to vibrate at this frequency till the energy is dissipated. So in simple terms, the string wants to vibrate at its natural frequency. Now, if we consider a forced vibration, this is different. The structure doesn't want to necessarily vibrate at this frequency, but its energy is being imparted at it. So forced vibration is when an alternating force or motion is applied to a mechanical system. For example, a typical example is when a washing machine shakes due to the imbalance of the load. I'll now quickly talk to you about vibration modes and what it is. This first mode is referred to as first flap, and it just shows a motion like this. However, if we change the frequency or increase the frequency, the actual motion changes significantly as well. So if we've increased the frequency now, we're now in a torsional mode, so you can see the actual motion of the beam is changing like this. Now, if we look at a compressor blade on a rotating machine, you'll see the mode shapes are a lot more complex and there's probably a lot more of them. Generally, the lower modes will be very similar to like the beam with a single flat mode going in like this, and then increasing the frequency will make it twist, and then maybe it gets a bit more complex. Generally, higher modes tend to be more complex, lower modes tend to be more damaging. On the previous slides, we talked about individual components having particular mode shapes, but a whole assembly can do as well. So in a rotating machine, consider that the shaft will vibrate and has various different mode shapes itself. So the first mode would be like a transitional mode, where the actual shaft will be going in this type of motion. Second mode may be a pivotal, where it actually, as it vibrates, it takes this type of motion. And then the third mode will maybe a skipping mode like this. Now, the actual influences on these tend to be the stiffness of the bearing structure. So what else could influence vibration? So if we go to the single degree of freedom model, we can try and understand the influencing factors that affect the natural frequency, and also hence the actual amount of vibration and the frequency of what it occurs. So looking at this model, we can see it has several different functions. Now this could be at a component level or at a whole structure level. So we have a mass, we have the force, we have a stiffness, and we have damping. To simplify this, or to explain it a little bit better, if you consider the actual suspension arm on a car, this is exactly broken down into its individual components. Now, how will these different things affect the natural frequency and hence the actual vibration? So if you increase the stiffness of the structure, then the actual resonant frequency, natural frequency, will increase. If you increase the mass, you will decrease the actual natural frequency. If you increase the damping, you won't change the natural frequency. You will change the rate of change of vibration. So it will effectively reduce the amplitude. If increasing the damping will effectively reduce the amount of vibration that you see, and it will be slow. If you increase the force, you won't change the frequency, but you may change the amplitude. With that, considering that, whenever you're investigating a vibration issue, there's always one of the key questions is always what has changed. So, has the force gone up, or has the damping gone down, or has something else changed on the machine? Has the mass changed? Has the stiffness changed? And how can that be related to what you're actually seeing? When we come to describe vibration, we can talk about it in several ways. We talk about displacement, which is basically the actual distance travelled by a body in motion. Velocity, the speed at which it gets there. Acceleration, and that's the rate of change of that. So if we just think back to the actual pendulum we had earlier, and you consider its motion, so with one cycle being from its starting point through to its midway point on peak displacement back to its original point of rest. So if we see which one of these actually reaches its maximum when, we'll see that the displacement is maximum when it's travelled the furthest distance. Velocity, however, reaches its maximum before then, because we're increasing in velocity and then we're slowing down again. Equally, if we consider acceleration, acceleration is at its maximum at its starting point and then reduces down. So we can actually look at the actual relative phase relationship between these, which is talking about the timing. So again, looking back to, if we plotted the actual displacement as it moved on this chart here, we can see that one cycle is 360 degrees, the time on the left, and we can see the point of maximum displacement is at its midway point. Now, if we look at the actual velocity, and when that reached its maximum displacement, you'll see that it actually reached its maximum displacement earlier. Now, if we talk about that, we don't say it's earlier, we talk about in terms of phase relationship in degrees. So we could say that the velocity leads displacement. However, in vibration terminology, it is conventional to actually talk in a phase lag. So what we would actually say is that the displacement lags velocity by 90 degrees, i.e. happens afterwards. So just to illustrate that further, if we look at the actual acceleration, we can see the acceleration is at its maximum prior to there. So again, if we compare the acceleration to the velocity, we can say that velocity lags displacement by 90 degrees. We can also consider relating different sensors in a phase relationship. So in order to do that, let's consider a rotating shaft. It's the shaft going around, it's travelling a counterclockwise, clockwise direction, and there is a sensor that for every single revolution generates a pulse. This may be referred to as a key phaser. It's effectively a once per revolution sensor. When that notch goes by, we have a pulse of energy or a vibration signal. Now, if we add a sensor and then look at the output from that sensor, if this shaft has got some degree of imbalance on it, then this heavy part of the shaft will try and pull it off center. And that will result in effectively, as this travels round, a sine wave occurring like this. So we can see from this blue probe, the point at which the maximum displacement that we're measuring occurs then. And if we compare that to our reference signal, we can see that we have a phase lag in this instance, so we're going against rotation of 315 degrees. So what we can also do is we can add a second sensor, and let's see how this works. Now in this instance, and we look at the signal from the second probe, we'll realise this probe actually reached its peak just after the key phaser pulse. And in this case, we end up with a phase lag of only 45 degrees. So they are absolute phase measurements comparing to our reference signal. We can also compare the actual signals to each other to try and understand how the vibration is moving. This goes back to looking at the mode shapes. If we wanted to see how signals were looking at compared to each other. So in this instance, we can see that the red line lags the blue line by 90 degrees. So let's consider vibration in rotating machines again. So one of the most common forms of vibration or source of excitation in a rotating machine is the imbalance of the shaft itself, and this will be at the rotational speed. One way we can predict when this will happen is by using what's referred to as a spoke diagram. So what we have here is increasing speed on this axis and increasing frequency here. And what I've also drawn on here to illustrate these is the frequency of the natural modes, or our free vibration points. So one thing that we should consider here is that we have the rotational speed of the machine, obviously is proportional to speed and frequency, gives you this black line, and that is your forcing. Now, when the actual forcing frequency coincides with a natural frequency, we have a resonant condition. We are imparting energy into the structure or into the machine at the frequency that it wants to vibrate. In some terms, on often rotating machines, this is referred to as the critical speed and corresponds with the natural mode of vibration. And this will occur when there is a coincidence between a natural frequency and a forcing frequency. Coming in here, I mentioned that the primary force will come from the rotational speed. However, in addition to this, depending on the component, forcing may come from other sources, such as a blade passing frequency or a gear meshing frequency. So what happens when the rotor goes through a resonance? Well, first, let's look at the actual amplitude of the signal. As we were approaching the resonant condition, the amplitude builds up. And this would, in theory, go to infinity if we were in free space. But because we have air or other damping properties, that will reach a maximum. When we go through the resonance, we start to come out the other side, and the amplitude will reduce. It's unlikely to reduce back down to what it was before. What will happen to the phase? Well, the actual phase relationship between the reference signal and the sensor, when you go through a resonance, will go through a 180-degree phase change. So what's actually happening here? Well, let's consider the heavy spot and the high spot theory. So again, we're looking back at our rotor, and we can see below the first critical mode that heavy spot, which will always be there, is at the same point of where the high spot is. High spot is the actual measurement we're taking, and when we're running below the first critical, the actual rotor will be rotating around its geometric center. When you go through a resonance condition, the actual measurement, the center of rotation will change from its geometric center to its center of mass. Effectively, the rotor is balancing itself, but what that does mean is that there is a 180-degree phase shift from the location of the measurement. Okay, I'd like to speak to you really briefly about measurement conventions. This is because vibration can be quite a complex subject, and sticking to conventions and the way we present data can make it a lot easier to actually understand it. So when we talk about looking at the shaft, we always try to refer to the phase angle against rotation. So for example, if the machine is rotating in a clockwise direction, our angle that we measure will be against there because we're measuring a phase lag. Equally, if the shaft is rotating in a counterclockwise direction, then we will be measuring in a clockwise direction. We can use notation to actually mark, when we start to analyze machines, we can use some quite simple notation to identify and understand the way a shaft is moving or a rotating machine is moving. So for example, we have here just a structure, and we can use this bubble light indicators. So here on this first example, we're saying our phase is 0, and we could maybe mark on there as well the amplitude of the signal. So a simple indicator could be that we've got a 0-degree phase change and 15 microns. We could simplify that further by just sort of adding 45 degrees and add a marker on there. This 180 would involve the line being marked down here. If we're just purely interested in the actual phase and that, we can simplify it further and just use the actual little leg on the marker, which is exactly what we've used just here. So you can see we can describe the way this two compressor machine is working, in that we have a phase of 0 at this plane, 180 at this plane, 180 at this plane, and maybe about what's that, 100 degrees, 120 degrees at this plane. So we also need to be clear on probe naming conventions. And what I mean by this is, which is left? Sometimes they're referred to as left and right. What about horizontal and vertical? And sometimes they're referred to as X and Y. If the probes are called vertical and horizontal, they're not necessarily fixed in horizontal and vertical positions. And what happens with the direction of rotation? Well, okay, if we consider a typical rotating machine where we have a prime mover, a driver, maybe a gas turbine, driving a gearbox and perhaps a compressor, where do we start? Well, the first thing, we decide how to actually look at the machine. So we say, okay, we're going to stand at the front of the machine and look driver to driven. So always look from the front, the driver, to the driven equipment. And then we're going to sort of look at our rotating machine and just consider what happens if we mount the probes like this and the machine is rotating clockwise. Do we describe them differently or not? The direction of the machine should make no difference. Equally, if the probes aren't mounted at 90 degrees, aren't mounted bang on horizontal and vertical positions, maybe they'll be mounted at 45 degrees or other angles. The key thing is they will always be mounted as an orthogonal pair 90 degrees apart. Now, it may mean that they're at 45 degrees like that. They may be all the way around and mounted on the side and the bottom, or perhaps even further round. The key things to remember, though, are as follows. Always view driver to driven. Probes are always 90 degrees apart. And always, Y, called Y, vertical or left, is always the first probe when you're viewing in the clockwise direction. So if we start up top, that's the first one. It's always going to be first. Okay, I would now like to speak to you a little bit about time domain versus frequency domain analysis and what that means. So if we consider a rotating machine, just illustrated here as a small power turbine spinning at 3000 RPM, which is equivalent to 3000 cycles per minute in US speak, or 50 Hertz. And we only looked at that as a vibration sensor coming off there, but we just looked at the broadband level on a trend monitor. Then we would just see we've got 20 microns of vibration on this illustration here. Now, while staying in the time domain, we could actually look in more detail of that signal, and we would actually see that it's a oscillating sine wave. It's plus or minus 10, which is your 20 microns. And if we measured the time difference, took the reciprocal of the time between these two peaks here, that would actually calculate back to 50 Hertz. And that's okay. If you imagine this is just a few cycles of vibration, if you try and look at many cycles of vibration, it makes it very difficult to look at them. But what we can do is we can look at convert this signal into the frequency domain. And if we do that, we do a fast Fourier transform of it. And here we have frequency along the x-axis and amplitude. And you can see here that we have the same 20 micron signal. It's very useful. As long as we know what the rotational speed is, we can say, yeah, that equals this. This is 50 Hertz, 50 Hertz. So that's the rotational speed vibration, that peak. We can make it easier for ourselves as well. If we read this signal in, we can actually change this x-axis so that it actually reads out in harmonics or orders, like so. So here you can see that we've got, instead of actually having frequency along the bottom axis, we actually have orders. So we can see Here we have very little information. We have more detailed information, but only for a very short period of time. And here we have some frequency content, but we can't necessarily, without knowing the actual frequency rotation, we can't relate it to how that relates to the machine. Whereas here we say that's actually a first order or a 1x vibration. So let's change the speed of the machine a bit and see what happens. Okay, so we've reduced the speed of the machine down to half. It's now running at 1500 RPM, which is equivalent to 25 Hertz. The vibration amplitudes are still the same. What you'll see is that we've got half the number of cycles over the same time period, and our peak in the frequency domain has moved down. Because we're still tracking the first order, the rotational speed has changed. This is still clearly a 1x response, which is what you would expect for normal behaviour of a rotating machine of this type. Okay, so we've doubled the speed of the machine now, and we are now saying we're now running at 100 Hertz on our actual speed indicator. And we can also clearly see that the vibration is still related to the rotational speed of the machine. Normal. So in the event that we have any fault conditions or something untoward happen, what does that look like? Well, we'll do another webinar to do a bit more about fault conditions and understanding them, but just as an overview, let's have a look. So here we can see we've still got a 1x signal, but we've got a strong peak coming in that's at twice the frequency. You can see this is at 50 Hertz, 100 Hertz, or if we look at it in orders, first order, second order. You can see that the sine wave is there's now two sine waves superimposed on each other. And when we look at the trend data, just the broadband thing, all this tells us is that the vibration level has increased. It doesn't tell you what's going on. However, it is difficult to interpret, but from here we can probably say, you know what, it's a high 2x response. There's a good chance that this may be related to an alignment issue, for example. Now here we've actually gone something to what's referred to as that's below 1x. So this is subsynchronous. Above here is supersynchronous. This is a synchronous speed, and then in this instance we've got something that's rotating, and it's rotating. So this vibration is happening slower than the actual rotation of the machine, and that's a particular fault condition. Again, we'll come back to them in another session. But hopefully that just gives you an insight into how we can present time domain data and frequency domain data. Thank you, and I hope you found that interesting and useful. My name is Rick O'Connor. Thank you very much.